Welcome everyone. This is the second lecture, second week. So now officially you have more of the summer school behind you than ahead of you. Congratulations. So you have accomplished a lot. You have learned how to build galaxies. You have learned how to access the largest databases. And you survived the zombies and the steampunks of the Comic-Con. Oh, and the War of Roses, of course. So that's right. That's right. So those of you who don't know me, I'm Tamás Budavári. I learned a lot last week, and I learned what steampunk is all about over the weekend. So what I have for you this week is a few interesting topics. At least I find them interesting. The first one lines up very nicely with what Gerard has been telling you about databases, and it concerns simulations and observations as well, how you search in these big databases, and how do you make direct comparisons of these simulations to observations. So what are the tools that will enable you to do this? And on Wednesday, we'll have essentially the whole day, almost the whole day, to the GPUs. So that's going to be intense. And on Thursday, everything else. So that's the plan. That's my plan for the week. All right. So today is spatial searches in astronomy databases, and which means multidimensional indexing. So who doesn't know what indexing is, or who knows what indexing is? Okay, lots of people know. Okay, so essentially it's a simple trick to speed things up. You do some work up front, and because of that, everything else later on becomes really fast. So imagine you have a big array of numbers and you want to look for a value. If you had that array sorted ahead of time, it would be very easy to find that, right? So instead of a sequential scan that takes essentially linear time in the number of data that you have, now you can do log n operations, things like that. Okay, so that's indexing. Okay, so let's start out with simulations. You can run simulations, then you can store simulations. So why would you want to store simulations? Okay, so simulations tend to take a whole lot longer than the analysis itself, right? So I asked different people, the number seems to be around 10, sometimes more. So it takes 10 times more to run the simulation than to do the analysis on that. And that's just the analysis that you thought of, right? And somebody else might have other ideas that they want to try out. So that's why you definitely want to store these. Now, why put them in? Okay, so these are just examples that you already know about, the Millennium, the Millennium XSL, and the Bolshoi, the multi-dark. These are all things that currently are served in not just file servers, but also very advanced through very advanced query interfaces, databases, and also turbulence simulations. Hopkins has a big turbulence simulation as well online. Okay, here's a nice plot of that. Okay, observing simulations. Okay, now you have this big simulation, and you'd like to compare this to what you measure as an observer. You have to do searches, all sorts of searches, typically spatial searches that have light cones involved, right? So you have some sort of three-dimensional shape, this frustrum, or whatever it is you call it, to figure out what are the interesting ones that would come into your comparisons. So if you want to do this, well, that's where you need to bring in the databases. Databases are nothing else but essentially a very sophisticated set of tools on top of your data, on your files, if you like, that allow you to make these searches fast and very simple. So you have heard about databases, essentially, from Gerard a lot. Okay, then once you have done these crude 3D selections and you do projections on the sky, then you want to fold in the very precise footprints of those surveys you want to compare against. That's where sky coverage comes in. So that's roughly the outline of the talk or of this lecture. I will walk you through how to deal with 3D problems in the database, and we actually have tools, and I'll show that can do this right now. So the Millennium simulations, the Bolshoi simulations in the multi-dark database are there for you to use, and these tools are available as well. So just go and use them. And so my hope is that you will essentially understand how this all works, okay? And also you can use it, okay? If very simple ideas, space filling curve, namely, is one that essentially maps these multidimensional spaces onto a simple one-dimensional thing, but you'll see how this all works in practice. And then we'll talk about the details. All right. So there are many databases, and Gerard mentioned this before. Which one do you pick? And it depends on really what the task is at hand. There are lots of simple databases that are fit on your cell phone, and they work fine for certain things. You wouldn't want to use them for big data, right? The most, even the big ones that are really expensive usually to get at are free for most of you to use for academic experimentation, research. They have limitations. They call the express versions, but you can download them. We can go online and download them. Don't do it now, but do it after in the afternoon. So you can play with those, and they have nice features. The biggest, or the most important for me when I look for a database for a solution is whether I can extend it, because there's never a tool that does everything that you want to do. Okay, so you will never find one that has it all. So you will want to have something that is very easy to extend. You can add on your custom user-defined functions or some other procedures. Now think of SQL, and I showed you how to query the databases. But think of SQL as a programming language. It really is. You have variables, you can create objects, you have it all. Okay, and it comes with very enhanced parallel I/O routines as well as indexing and so on and so on. Okay. So what we're going to do is take an existing database. In this case, it is a SQL server, and we're going to customize it. But before we get there, we start essentially the abstract geometry and the concepts that we want to put in. In this case, it's query shapes. Okay. So it's a very simple problem. You have this big simulation, and you want to be able to cut out certain parts of it. You want to find halos. You want to do a virtual observation of the simulation that you have just done. How do you do this? Well, you start with something simple. You start with these geometric primitives that are spheres, boxes, cones, you name it. Okay, and you start building from these. Okay. It turns out, well, the simplest thing you can think of is a function you need for every one of these primitives that gives you, what point is inside. Okay. It gets a little more complicated than that because of numerical uncertainties. So you actually want to have a struct that describes all the possible combinations inside, outside, and on the boundary. So it's not just a binary decision at this point. And in addition to this, you also want to be able to describe how these things relate to boxes, because that's typically what the simulations are in, periodic boxes. So these are the few functions that any primitive would have to know about, how to figure out what this bounding box is, whether it intersects with the box or not, and whether the point is inside or not. And if you can do this, then you're good. You can add new primitives to these frameworks very easily. Now, it turns out that all the composites that you could build, union, intersection, difference of these primitives, can be also very simply implemented in a generic way, just using the same methods. Okay, clearly a bounding box of a sphere minus a box would be the bounding box of a sphere, or maybe a little smaller, but that's just a second order correction, right? You don't really have to go there to make many of these things really fast. So with that, you can do a whole lot. Okay, and this looks very nice in SQL if you can implement it by these user-defined types. So the sphere in this case is a type that is created in SQL as a variable. And then you can call its methods that it says, is this point 1.123 in the given sphere? Is another point in the given sphere? We can have a box. You can have a box created from just a string representation. These are very powerful things that you can just do in SQL, happens automatically, and you can use them. So then you can also have generic shapes that generalize and abstract the different kinds of shapes from you. And the simplest way to create those is just through these the string representations. Okay, so you can just create unions with a function, intersection, and so on, and then run these queries. I'll show you later in how this works. Or you can just use the parser itself, which also supports the keywords union, intersection, and difference. Okay, so these are very simple primitives that we add to the language. And with that, we can actually enhance this functionality quite a bit. Okay, so then what's indexing? We already talked about it very briefly. Formally, it's essentially almost like a table. It sits in the database. It's kept consistent with the data that you have. And it contains all the things you want to sort on, as well as things that you want to include in the index. Why would you want to include things in an index in addition to what it was sorted on? Well, it's all about optimization. If you want to run a query that touches certain columns, then as long as everything is inside the index, there's no need to join it with the original big table, and which will slow it down. It's called a bookmark lookup. So essentially efficiency. I think you got the idea. Okay, so how does it become multidimensional? Well, you have to map somehow the multidimensional space onto a simple index, okay, which is one-dimensional. Right? And the trick here is space-filling curves. So if you don't remember anything from this talk today, then remember space-filling curves. They're useful and they are available. So use them. There are different kinds, and in fact, you can define any kind you like. There are classic ones that I'll quickly show you. Okay, so this is a Peano-Hilbert curve. Okay, it's a classic example. It turns out to be optimal in many ways. What happens is that you have a volume that you would like to go through, right, with some given resolution. Okay, everything is discrete. It's computers. Okay, so you can go around this. You can chop this box up into 4 smaller boxes, or if it's in 3D, then it's 8 smaller boxes, and go through it just by doing this U shape. Okay, and then you recurse into every one of those boxes, and go through every one of those boxes as well at a higher resolution. So now this box will get recursed into and does the U shape like this, okay, and then this one goes like this, and so on. Okay. So you can imagine how you can keep on doing this, and in every time you go to a higher resolution, and in the end you just have a single parameter curve that goes through the entire space, and it will be in the vicinity of any point with the given resolution. So that's the idea. Of course, it works in 3D as well. Okay, this is how it works in 3D. Okay, very simple. It's kind of pretty too. Okay, here's another one, the Z-order curve. I guess you have to look at it like this to have it as a Z curve, but other than that. So this one has more jumps in it, as you can see. It doesn't go like this, it jumps back. And even here at the high resolution, you see there are big jumps coming in. So you can probably see that sometimes this is not quite as optimal. There are actually very detailed studies that look at the properties of this curve and try to establish which one is better and worse for different kind of studies. Namely, you have to look at the correlation functions. What we will have to look at is essentially how these curves interact with our query shapes. So that's where this becomes important. All right, so divide and conquer. How do I do now a search against this billion or 10 billion row database? Okay, I have these points all scattered around the volume. Well, I have a circle coming in. That's my search. Okay. I start recursing into this volume. Okay. The first step is right here. Okay. I see that this box intersects my circle, or at least partially contained in my circle. There's a collision there. Right? So what you do is you recurse into the subcells in that. That's the second picture over there. Again, you keep on going. Soon you realize many of those cells that are white in this case can be excluded from your search. Right? So the points in here will never get looked at. And in fact, all the points that are inside completely, these blue cells that are inside my query, my query shape, I know that all those are guaranteed, all the points in those cells are guaranteed to be in my query. So there's a lot you can gain by just doing this. And find this, and eventually you get to a representation where you have the boundary of your query shape approximated by these, and then the inside. Okay. Any questions about this? No? Okay. Here is Gerard work on visualizing how this looks in 3D. So if you had a 3D sphere and had an inside and outside approximation, okay, then this is what you get. Okay. The inside is smaller than the shape, of course. The outside is bigger than the shape. Okay. So it turns out that every shape, what you can ever think of, will translate onto ranges in the space-filling curve. This is where things go in and out. So for example, if I have a shape that looks in this part of the volume, right, then it translates into a single interval. It goes between 0 and 3. Okay. If I make this higher resolution, if I recurse into level 20, it's still going to be a single range, okay, because that part is just a single range. If I do this, that's still just a single range. If I do this, now this is now 2 ranges, right? So this will be a range from 0 to 3 and then from 8 to 11. And of course, again, you would want to recurse into really high resolutions to typically you want to get good covers. Okay, and then any shape will do, right? So they will not always be perfectly lined up with your cells, and you will have multiple of these ranges, but you won't have too many. But essentially, all you need is a number of ranges, just pairs, min, max, key value pairs, that will essentially approximate your queries and make these very fast. Okay, so of course, with simulations, you have periodic boundary conditions. Okay. It means that you don't really just want to search one box. You want to search infinite number of boxes, and all the boxes that there are. So especially if you have a light cone. Right. So what happens is that conceptually, you really just cut and paste the box all around, and you can look for overlaps with your query shape like that. That's actually turns out very efficient if you do it right. You can always figure out the bounding box for your query shape, and then figure out what's the replication level that you would want to go to, and essentially calling the same type of recursive or iterative algorithms that you do with establishing the covers, these approximate shapes using the IDs. The same technique will do to find which periodic box you would want to look into. Okay? And if you have evolution, you have redshift evolution, then you can also look at those boxes at their redshift. Okay, so this is what here. This is a light cone going through a large volume, and this is how these segments of the light cone pack into the single simulation to overlap, to avoid the overlaps and so on. Okay, so this can be all done, and it's very simple. Okay, yes. 2 slides?
Yep. Keep going.
Oh, 3 slides.
That one, sorry.
Okay.
What about if the min and the max are the same? So like if I wanted to look at cell number 3.
Yeah, no big deal. So I mean, in this case, for example, you would have cell number 3, right? So that's 3 to 3. It's going to be higher resolution typically, so you don't get those very often. But yes, no big deal. So then just 3 and 3, and you know that that cell has to be looked at, but nothing else.
So like you can look at anything. You can look like along one of the diagonals or an L shape.
Oh yeah.
10, 8, 7.
Absolutely, yes. Yeah, so the tool will essentially give you, the algorithm will give you what are the cells that you have to look at, and what are the ones that you can just discard and you don't have to worry about. Okay, that's the key idea here.
So the library doesn't, for example, you don't have to figure out the ranges. For example, say in this curve, for example, you might have IDs which are very far apart, but the objects or the cells lie very close to each other, for example. Do you have to figure out the ranges by yourself?
You don't have to do almost anything. I'll show you how it works in practice. It's very convenient to use. But you do have to know about the cover, that it exists. So essentially what happens, you have to use these ranges that come out from a function automatically. I'll show you. In fact, this is the query that I wanted to show you. This is it right here. Why don't I just go and show you this in action, because we don't have a hands-on attached to this. Okay, so I don't actually see my screen. Here's my mouse. All right. So here it is. This is running the Millennium on my laptop. Okay. So I can create these shapes and run these that I showed you before. This is just now a sphere testing against points. This is a box testing against points. Not particularly interesting. But now here's what becomes kind of nice with the parser in place. Okay, so those strings actually create those objects in place. It's a memory object, and then you can call those functions on it and just get like 0 and 1s that are the booleans. Okay. Now the simulations are similarly stored in objects. They are created from a given cosmology and a box, which is it's a boundary. So here is the box. This is the cosmology with its parameters over there, and the simulation is defined as a function of those two. Okay, it has a string representation. It looks something like this, and then you can get a cover for this. Okay, so here I have the simulation sitting here in the body of this, as an argument of this function. And I have a query shape, in which case this is just a simple sphere. And this tells me what the level I want to recurse into, how deep you want to go, what the resolution is. So when I run this, I guess I have to run the whole thing to create the simulation. Then I get this table that lists, you see the mean, the max. This is where you go in and out of the shape. And the shifts. Now the shifts tell you which box it is, because it's periodic boundary condition. Right? The shift x, y, z are actually in H inverse megaparsec telling you that you have to go that way by a whole box or multiple boxes. Yeah. Okay. No questions about this? It's very simple to use. And then you can also wrap these things into functions. So this is a little convenience function that Gerard wrote that gives you the millennium simulation that has its cosmology and has its box and everything in it. So I can just create a cover for it like this. Okay, so now again, this is a query shape, just a simple sphere. All right, so here's a more complicated query that it actually is something interesting. Okay, so you haven't seen this probably. The with extension, the with keyword defines a common table expression. Essentially, what you have there is just like a table. So you can use, in this case, the cover as if it were a table, and that's what we do down here. Okay, so the cover is, for the purpose of this query down here, is just a table. And that cover is joined with the MP a halo table that has the positions in it. Okay, and it has the Peano-Hilbert curve indexed. So the pH key that you have on the joint condition of the two tables is something that is indexed on. So these things will be really fast. And the key value, the key min and key max is coming from the cover. This join will run very fast. Okay. So you get 28 rows in just essentially instantaneously. Okay. Anything more complicated than this is something that you will automatically learn. Because as you write your query, you will just evolve them, and they do get a little bit more complicated, but not that much more. So this is pretty much it. Okay, let's just go back to, if I can find my way. All right. So that's the same query that you just looked at there. Yes? Yes, that's right. That's right. This is something that you can do actually in SQL. Right? So you can add in the pH keys. There's a function that calculates it for the X, Y, Z, and then you can index it. This is just all a few lines of SQL. Okay. And this is a more complicated query. So like I said, there are online interfaces that you can go to and run these things. And there's the multi-dark simulation and the Bolshoi. And this is a slide I guess I put together last year. The Indra simulation was coming soon now. It's 10 million hours away. Is that right? It's 10 million hours away? Yeah. That's soon. So this is a screenshot of the Millennium XSL website that Gerard showed. This is the version that actually the spatial search enables. So when you browse around and click on something, then spatial search is fired up against the database, and in 30 milliseconds you get back all the halos that are relevant for that part of the sky, or that projection at least. So that's this search engine actually fast enough to enable interactive features. Okay, and there are web services, and this is very important because now you can not just interactively but also programmatically access these simulations. So you can be sitting in a cafeteria and working on your laptop and interrogating this billion row table or this 100 terabyte database somewhere else, across the country or across the world. And this is very fast to do because of these spatial searches. You can inject probes anywhere you like in these simulations and get the velocities, the densities, and so on very quickly. Okay. So that's the spatial part, the 3D part of the lecture. And now I will switch to the sky coverage, which is very similar in its philosophy. And in fact, that was the one that was first written. But it has differences when it comes to defining shapes on the sky, and as the sky coverage or footprint question that I wanted to also discuss, that you know how to handle this. So any questions about the 3D things? No. Okay. All right. So you always have sky coverage, right? I only know one paper, one observational paper that had no sky coverage. This is the one. I don't know if you know this one. This was done by the Galaxy Zoo team. No? Authors are Marvin and Trillian. This is a discovery of a very unusual galaxy cluster, a new type of galaxy clusters. No? Okay. All right. So that's the only one that has no sky coverage probably. Everything else has sky coverage. So you have to really learn it. You can all read it, right? Okay. Yes? No? Who cannot read it? Okay. So the spatial geometry is complicated, and I just had this slide on before. You really have to think about this to do it right, because observations can get complex, and they do get complex. So you have to look for a good solution, and the solutions are actually plenty. There are different approaches that you can consider, and people have been looking at them. You can think of pixel maps, sensitivity maps, You can think of vector graphics type of solutions. And there are all sorts of hybrid solutions as well. And I just wanted to make sure that you see where they all fit together and what their different purposes. Okay, so if you make an observation, okay, you always have a footprint or a sky coverage information that comes with it. The astronomers are very careful about their sky coverage information, and they build tools that will store it immediately into the FITS files that you save. Okay, this is called the WCS, the World Coordinate System. Okay, there are papers to look up on this if you're interested. Now, this is great as long as you have one image. Okay, but as long as you have two images or more, then you have several coordinate systems. And now it's not so obvious how you would go between back and forth. Okay, so we'd like to do something that goes beyond this very simple, actually quite expensive way of representing the footprint. Okay, so you maybe have a common pixel scheme, right? Maybe you want to pixelize the whole sky somehow. Simple. All right. The simple. How long has it been here?
Just walked in.
Okay, good. Okay. So, all right. I'll watch out now. So the simplest thing you can think of is like an atlas, right? You have the pages of the atlas, and that's it. If you want to go to a different place in the sky, you just flip the atlas, and you're on a different page. And people actually use this, right? So surveys would build up big stacks on different parts of the sky. And then, of course, those stacks will be overlapping, so you have to define how to cut between the pages. So on an atlas, you would have a country, and of course, you would see all around the neighboring countries as well, but those will be either colored differently to make sure that you see that they are different, or some other way the borders are shown. Same thing happens in astronomy. Now, there are also other type of pixelization schemes that people have been using for different purposes, and they usually had reasons to be analytics that motivated these pixels. So the Sloan pixels, for example, were invented so that they would match the Sloan footprints and enable certain searches, but for everything else, they would be approximations. Now, there are pixelization schemes that enable fast analysis, like the HiPACC that does spherical harmonics very well, or the Igloo. But again, if you want to go that way and represent sky coverage with these, you end up having lots of pixels in a hierarchical fashion that you have to represent somehow. And it's very, it's always approximate, and it's not always simple to use. Right? So the standard way to deal with these kind of things is what Google or Virtual Earth does. Right? So you create this image pyramid, and you create a service that goes with it. So people can go to this website or go to this service and look up things. Right? So you can point your viewport to San Diego and look at San Diego, or you look at Andromeda and you look at Andromeda. Okay. But they're good at storing continuous data on the sky, but if you want to describe just binary information where observation was taken and where there was none, then they are not very efficient. And so you would like to have something else. Okay. In particular, because it's hard to combine these things, right? If they are separated in different places. Okay. So the alternative that I would like to explain to you is something that works very well. Is essentially equivalent to drawing on the sphere with equations or vectors, kind of like vector graphics in 2D versus bitmap. So the previous one is bitmap graphics or pixelization, and now we are talking about vector graphics. Okay. So in particular, the sphere is complicated because it just goes around. You know, if you go that way, you come back this way. Okay, it's a closed surface. So if you try to do polar coordinate system or something like that, then you always have problems at the poles. Now, GIS systems, cartography doesn't really care about that, right? Nothing on the pole. Or if they do, then they try to chop things up, such things that are not perfectly aligned, in the middle of the ocean. Okay. But for astronomy, we do care about the whole sky. Okay. So it turns out that if you just abandon, the notion of using 2 parameters for the sky and use a 3D vector, normal vector, then everything is golden. There are no poles, there are no projections to worry about, no singularities. So that's all you have to do. Okay, so now the simple primitives, again, similar to the sphere and the box that we had in 3D, to draw on the sphere are essentially the plane. Okay. If you take a plane and you cut the sphere with that, what you get is a cap. Or on the surface of the sphere, you can call it's a small circle. Okay. It's called a half space because the plane actually divides the space into halves, and it picks one of them. Right. So if the plane was oriented that way, then you would pick essentially the whole sky except for that little cap. Again, because it's closed, so you don't know which is inside or outside unless you specify a direction. Okay. So using these caps or circles, you can very quickly build up complicated shapes. And these are called the convexes. Okay? So the intersection of all these things will be convexes. If you wanted to have something that is a rectangle in the sky, an observation in a tangent plane, that would be just 4 half spaces. Okay? That cuts out essentially the perfect rectangle that you just observed. There's no approximation there. It's accurate. Then on top of that, using the convexes, you can actually build up more complicated things that you couldn't do with just intersections, and these are called the regions. This is where the spherical geometry comes in. Now, why do we do it this way? There are other approaches to consider, but it's simplicity. Okay, so to test if a point is inside a half space, all you have to do is take the half space's normal vector, the orientation of the space of the half space, and take the dot product of that vector with the points that you want to test. Right? That's again a 3D vector. That's normal vector. All you do is take the dot product, which is the cosine of the angle between them, essentially, right? And you compare the dot product to the offset of your half space. Okay, it's a very cheap operation to do. That's the containment test. Now, how do you test if a point is inside a convex? Okay. Well, it's inside if it's inside in all the half spaces. Okay. So similarly, the region contains a point if any of the convexes contain a point. Okay. So it's very simple. Now, in addition to that, you can actually use this representation very quickly to create complicated regions, essentially create the intersections mechanically. Right? If you wanted to intersect 2 convexes, all you have to do is concatenate the half spaces into one convex, and that's your convex. All the intersections are just automatically implied, then it works. If you wanted to take the union of 2 regions or 2 convexes, well, you just have to concatenate the convexes themselves. So it's essentially two nested lists. A list for the half spaces, that's a convex, and a list for the convexes, which is the region. And everything is on top of that. Now, there is a little bit of extra magic going on in the library that implements this. I will show you this shortly. Because you want to make sure that you can create unions. This is a union of 2 circles where there is no overlap. So you get rid of the overlapping regions, so the coverage is unique. So in this case, we have a circle in this crescent, this moon shape that's next to it. Okay. So this way, all convexes are separate, they're disjoint, and you can calculate the areas analytically and just add them up, which is something that also this library that I'm going to show you provides. Okay, so, all right. So difference is another one of these Boolean operations. It turns out to be very useful and often used. This is where the regions come into play to see if you wanted to just use convexes to describe everything, you couldn't do differences because the difference of two convexes is not a convex anymore. Okay. The difference of two convexes right here ends up being 4 convexes in this case, which is a region. Okay, so union of 4 convexes will be a region. Okay. Again, these things can be mechanically created. It's very simple to do and very powerful. Okay. I will mention this very briefly. So just because you have to appreciate how this vector graphics is actually providing you with very high quality representation and very complex representation of everything you can think of. So you can, with this, represent something that is the whole sky or something that's sub-pixel. Okay, you can just keep on zooming in. I mean, the only limitation that comes in eventually is the precision of the double precision that you use to store these 3D vectors that are underneath the whole library. Okay. This goes beyond. Okay, so the library itself that we created to do this is something that's available online. You can download it and use it on any operating system you like. It's .NET, which means that you can run it on Mono, which is an open source .NET implementation on Linux, or your Android, if you like, and Windows. We also recently created a C++ implementation that runs as well very fast, and also have Java available. So these tools are actually there for you to use. Okay, this is, I briefly mentioned this, the imprecision that comes into play, and it's essentially, we looked at the numbers. On the sky, on Earth is 30 centimeters, the resolution, what you get from double precision. If you wanted to look at the sky, essentially it's hundreds of an ACS pixels, the smallest cameras that you, or the highest resolution observation that you can get are still not the limit. Okay, so here's a representation, just a plot of Sloan and Galax footprints on top of each other in a strange stereographic projection. Because you have the equation stored, right, you can create any representation of these things you like. You can have 8 of plots, you can have stereographic plots, you can zoom in and so on. So this is the north, essentially that's most of the Sloan there. Out there is the southern sky with the stripes, the 3 stripes, and then the little honeycomb shapes are the primaries of the Galax survey. Okay. So how does this look in SQL? Okay. So very much like the 3D. In fact, this was written earlier with previous technology. So here you actually get to see the row SQL type, which is var binary. It's not a user-defined type. In this case, it's just the blob where the object is serialized into. And it can be very quickly read back in to use it for get the area, test the containments, and so on. Actually, there's a new wrapper on top of the library that uses the same UDT type as well, UDT style as well, where you can create a region and do it the same way. Okay. And then on top of this, there's a service that we built, which is essentially a public repository for all the regions that people, or all the footprints that people created. Okay, so the sky coverage information can be stored and looked up. So if I create this, okay, let's go here. Okay. That's the service. And here you can go and search for keywords, objects based on position, names, and so on. You can look at Sloan, footprints, other things, and you can click on these. You get information about what the area is for these things. You can go on to download them. These are very simple ASCII files. Again, the power of this, you can throw this at any service you like, and potentially they would give you back the results based on that. Okay, you can plot this up right here in different ways, ATOF and stereographic. We just didn't go further. You can walk around, see what's here or there. You can zoom in. There's nothing there. And then you can also just log in, if you like, and create your own footprints. They're sitting right here, all sorts of tests. You can make them public, if you like. This one is not public. I can go and modify and make it public. It is public. No comment provided. I should probably comment on this if I make it public. Okay. And we also have an editor where you can create these things. Okay. So you say you want a new region. You can create a polygon where you just specify what the points are. It can be any polygon. You just have to go around the points, around the polygon to save all the points. And can be array and deck pairs. Oh, I know what this is. It's safety. My browser is very secure. Okay. So I have a polygon, have a union of that with a circle. Okay. You can save it, you can plot it, zoom on it. So you see now the two simple convexes are put together in this complicated region that actually is three convexes now. There's no overlapping parts, so then we can just add up the areas and get the total area of this. Okay. I think you get the idea. Here we go. And it also has web services, so you can program against this. Okay, so you can write your Python code and create these footprints, download these footprints, and throw them around. Okay, this was a big deal in 2006. So it made the ADAS Proceedings front cover, and since then we've been looking at all sorts of different solutions. So what I will talk about next is two hybrid solutions where you take this vector graphics and combine it with pixelization. Okay, so one of them is going to be the search, and the other one is going to be something else. I think I start with that first. Yes, here it is. So this is a small part of the first survey that Rick talked about. Okay, which is essentially a number of pointings, beams that you can approximate with circles. What happens is that you have zillions of circles on top of each other overlapping 12 times. Okay. So it gets really complicated, and there's no simple way to simplify things. So what you can do is you can create a mashup between some pixelization scheme for which you can describe the pixels with geometrical constraints, essentially these half-space convex regions, and use that to substitute the middle of the survey that essentially is just completely covered. Okay, so that's something that that you do essentially the same way you would do with search. You divide and conquer. You drill down to figure out the cells that are completely covered, and then build up by merging the ones that are joined and can be stitched together very easily. Yeah, something you couldn't do with the circles. Okay. And the other one is the indexing the sky. This is called a hierarchical triangular mesh, or HTM. Okay. If you have run any type of spatial search against the Sloan database, you have been using this library, the hierarchical triangular mesh, which is just another space filling curve, except now you are indexing or going through not the three-dimensional volume, but the 2D surface of the sphere, the celestial sphere. So what you start with here is the octahedron, and you essentially divide every triangle into 4 triangles in every step. And of course, as you go down very quickly, you get a very good approximation of the whole sky. Okay, this is just shown like this so that you see, but it actually is all done with spherical triangles, right? And then you get a query, just like we had it with the 3D case, in this case a circle, and then do the same thing that we had before. You have a cover for the outside, you cover for the inside, and you can do the spatial searches just like that. Okay. And this is just so you see some real regions from Sloan. Okay. This is how one of our simple regions look like. You have the half spaces all looking here. These are the equations that are required to describe the shape. Okay. This is the convex that is built up by those half spaces, and right here is essentially 2 different covers for that at different levels. So you see the gray area triangles are the ones that are completely inside, and then the white ones are that are approximating this region. Okay. Now HTM filtering is that simple. Okay. Just like we had it before, now we have a function that takes the region description, which is a string, okay, and turns it into a number of ranges. Right? If I ran this, you will get again the min and max, min and max, min and max that I can use. They call now ID start and ID end, that I can use to join my 500 million row table, and quickly pick out the ones based on this index that are inside this region. Okay. Any questions about this? No. Okay, good, because I'm getting to the end. Essentially, using these, you can not just only store the simulations, but you can also make them into a searchable form that enables these spatial searches really fast. Literally, you're looking at 30 millisecond response times for the kind of searches that people typically run. Of course, if you want to create a big virtual simulation or a virtual observation of a simulation, that will take longer, because you will have to look at all the objects and shift them to the appropriate redshifts and appropriate frames. But then once you have that, then you can use the sky coverage information to cut out exactly the shape of a observation and compare that directly. So if you wanted to do spatial statistics that you'd already discussed before, that is simulating all the artifacts that an observation would have, then this is how you would do it. Okay, so this will enable the direct comparisons. Okay, so the key things here to remember is that the space filling curves will help you if you have any of these multidimensional problems. And the other one is that the tools are available. So if you want to use these, you can just go to the databases. So that's where I stop today. Thank you. Any questions? Yes.
Any observations preloaded in there? Like, can I go and get a candle survey just without having to type in all of the things that I want?
So, right, the question is whether there is any observation data in there, but the question, what do you mean by there? So this is a tool that is deployed in essentially most of the databases that you would want to, you will be able to query. So if you want to do simulations, then the spatial 3D library will be available. If you want to go to Sloan, Galax, the Hubble Legacy Archive, or other the UKIDS, there's a whole list of surveys that actually use this library. Then the spatial library, the spherical library, will be available for you to use. So the answer is yes, but not in one place, because these are separate databases and they just live their own lives. The beauty of having this compact representation of the shapes, both in 3D and on a sphere, is that you can actually take these descriptions and take it to another survey or another database, if you like. Okay. So now, how you bring them together? So you do have just one sky to join them all, right? So we'll talk about later how you do cross-matching, and that's where you would probably want to bring together different observations. Now, clearly simulations are not something that you compare, object by object to the observations, but statistically, you can do the same searches on the different archives and then compare those. Okay. Any more? If not, then yes.
How many database systems provide for user-defined functions?
They all do user-defined functions. What they don't have often is the capability to actually create a user-defined function that returns a table. So in this case, these covers are coming back as a table because you have to have the ranges all represented. And that's something that they don't always provide in a simple manner. Now that's changing. I mean, I think the customization is getting easier and easier for all the databases because people realize that that's something that they must do. However, right now we have to work with the tools that we have. And it turns out that the simplest tool and a very powerful tool that scales well with the big data that we had looked at so far was SQL Server. And in there, essentially, it really is beautiful. You write a 10-line code in a high-level language, just like Java. C# is just a better Java. Then you compile the library out of that, the dynamic library, and just drop it into the database. And there it goes. You can call the functions, and you can use its functionality. So the Hubble Legacy Archive, that the cross-match project that Rick mentioned, was completely coded in SQL Server. The whole pipeline is running essentially in the database, all written in SQL with some extensions that are just like these. Simple things that we had to code in a procedural language and just drop it into the database. Yeah, so that's a very powerful feature. Yes?
Compatible with the normal types of databases like Postgres and MySQL, or is it limited?
Right. So when you develop something, you always have to figure out how much time you have and what you want to target. So our primary target was, of course, originally Sloan, and then later the Millennium simulation. Now it turns out that the language we chose and the whole procedure that we followed was the simplest possible one. And now that we are actually porting these to C++ and MySQL, we find out that those are doable, but much more difficult and less elegant to use. So I think there is room for improvement on both ends, both our end to get the tools running in those databases, but also the databases should be allowing for better integration and better customization. So and hopefully that's going to happen as well as we work toward this goal, and then all these databases that you mentioned will have this functionality enabled or integrated into quickly. Yeah, so we have C++ code that was actually created to port this into MySQL, and it's in the works. Yeah. Okay, no more questions? Well, thank you so much.